This section takes a look at titrations. A lot of this we already know. We know what the titrant is. That's the stuff that's in the burette. Usually it's known. We know the unknown stuff in the Erlenmeyer flask is usually the analyte. Now they can switch that around. Your analyte could be known while your titrant is unknown, but that's almost always the way it works. You have your equivalence point. This is the stoichiometric ratio point. It's a point where the stoichiometry of your titrant and your analyte are so that you have enough of one substance to completely react with the other substance. You have your indicator solution, which is a weak acid or weak base that will turn colors at a specific pH. You have your endpoint. This is where your indicator changes color. Usually you have it set up so that it's about at the equivalence point, or it's a little bit after the equivalence point, although it doesn't have to be. You have to pick the right indicator for that to work. And you have, if you graph out your pH versus your amount of titrant that you're adding, then you get a pH titration curve, which is what we did in our last lab. If we take a look at a couple of pH titration curves, if we take a look at this first one here, we're starting with a strong acid. So we're starting over here at a pH of about 0, 1, somewhere around there. As you add a strong base, nothing happens for a while. That's because the base is getting used up by the acid. But when you reach that point where you've added just enough base to completely use up the acid, and if you go any further than that, you're just adding more base, you get this jump in the pH. It's going to level off around 14-ish because you have a strong base. Your equivalence point is going to be right about 7, because that's when this is going to cancel out. If you were doing a strong base, strong acid titration, you'd have the same sort of thing, only it would look kind of like that, and your equivalence point would still be right about 7. Now, if you're doing a weak acid, strong base, or weak base, strong acid, pH titration curve is going to look a little different. For one thing, you're starting in a different place. You're starting up higher. You're dealing with a weak acid, so its pH is maybe about 3. It's still going to level off for a while you add strong base, but at some point, it's going to jump up because you're going to add enough strong base that it is going to that's going to cancel out that weak acid, and it's going to level off at a nice high point. I think it should be a little bit higher than it shows in this graph, maybe around 13 or 14. Your equivalence point is going to be somewhere above 7 this time because you're adding a strong base to a weak acid. If you were doing a weak base, strong acid, you would start out somewhere below 14, maybe around 12. And again, it would level off for a while, then it would jump down, and you would end up having it level off down here around 0, around 1, because you're adding a strong acid to that. Your equivalence point is going to end up being below 7 somewhere. And this is the basics behind how these weak acid, strong base, or weak base, strong acid titration curves look. Now, when doing problems with strong acids, strong bases, these are pretty straightforward. We've done a lot of these already, all right? These are just plain old titration problems. Use the molarity and the volume to find the moles, use the equation to find the mole ratio, and then use your moles and your volume to find your new molarity. You can also use this to find pH, which is what we're going to do with this example problem here. We have NaOH, we're adding HCl to it, so strong acid, strong base. And we start the same way we started all of the others with our balanced chemical formula. Strong acid, strong base titration problems always have the same basic balanced chemical formula. It's going to look something like this. Now I have 50 milliliters of 0.1 molar HCl. I'm going to add 49 milliliters of NaOH to it, and I'm going to add 51 milliliters of NaOH to it. So let's start with the 49 one. First off, let's see how many moles of HCl I've got. And then let's see how many moles of NaOH I'm going to be adding to this. Now, when we look at this, we see that we have 0.005 moles of HCl, 0.0049 moles of NaOH, and that means that NaOH is going to be my limiting because I have less NaOH than I have HCl. So that means I'm going to use up all the NaOH. I'm going to use up 0.0049 moles of HCl, and what I'm left with is 0.0001 moles of HCl. Now to find the pH, I need the concentration of the hydrogen ions. So that means that to find concentration, I need to divide this by volume. I added 50 milliliters to 49 milliliters, so I've got 99 milliliters here. And I can use that to find my concentration. And then I can use that concentration to find my pH. So before, just 1 milliliter before we hit equivalence point, which will be at 50 milliliters, we have a pH of 3. So it's still pretty low. Now if we added 51 milliliters of NaOH, so we've gone 1 milliliter past equivalence point, it's the same kind of thing. We're still starting with the same amount of HCl that we were before, 0.005 moles of HCl, only now our NaOH is going to be 0.0051 moles of NaOH. So this time it's the HCl that's your limiting reagent, and what we're going to have left over is hydroxide ions instead of hydrogen ions. So this time if I find the negative log of this thing, this time I'm going to be finding the pOH instead of the pH, and I'll find that my pOH is equal to 3 this time, which means my pH is actually equal to 11, which if you had calculated this out earlier, you probably could have guessed this. Alright, it's going to be the same distance from 7, only in the opposite direction. You add 0.01, if you add 0.0001 moles either direction, it's going to change it by the same amount either way. Just one goes one direction, one goes the other. Now when we start dealing with weak acid strong base titrations or weak base strong acid titrations, this is where it's going to start getting a little difficult. They're both work the same way, and so if you know how to do one, you should know how to do the other one. And so we just need to kind of learn a few set steps, and we should be able to figure it out. Sometimes it's easier to think of this as getting broken up into 2 steps. In your first step, you're just treating it kind of as stoichiometry, just like we did in the last problem. And then in the second thing you're going to do is treat it like an equilibrium problem with equilibrium expressions, Kas, all that good stuff. Your initial pH is going to depend on what you start with. If you're starting with a weak acid, like if you're doing a weak acid strong base titration, that means you're putting a strong base into a weak acid, then your initial pH is going to be dependent on the weak acid. If you're starting with a weak base, it's going to be dependent upon the weak base. It just depends on whatever you're starting with. But once you start adding strong bases, your pH is going to change. And so you have to consider what's going on in the reaction, and then you have to calculate a new pH based on this. A good rule of thumb to remember is that if you're doing a weak acid strong base reaction, your pH is, your equivalence point pH is always going to be over 7. If you're doing the opposite, weak base strong acid, it's always going to be below 7. Now up to equivalence point, your pH is dependent upon the weak acid, but after you've hit equivalence point, then your pH is determined by the base, because there's excess base now, so that's going to determine the pH. Now one important question for these types of reactions is why is the pH greater than 7 when you're at equivalence point? It's because the anion of the weak acid is a base. And so whenever these two are reacting with each other, you're making a weak base. And so whenever they completely neutralize each other, you don't have just neutral stuff in there. You have this weak base sitting in the solution. The stronger that anion is, then the higher the pH is going to be at the equivalence point. So let's take a look at an example problem. When looking at these problems, the first thing that you ought to notice is that you've got a strong base, NaOH, you've got a weak acid, acetic acid. That's a clue to you that you need to treat this as a strong base weak acid titration. Start this out the same way you start everything out, balanced chemical formula. And we start out by treating this as a stoichiometry problem. We have 45 milliliters of 0.1 molar NaOH. We have 50 milliliters of 0.1 molar acetic acid. So first we got to figure out the moles of both of these that we're dealing with. So molarity equals moles over volume. So looking at this, we see that we have less NaOH than we have acetic acid. So NaOH is going to be our limiting reagent. It's going to act essentially to completion. So we're going to use up all our NaOH. and we're going to use up 0.0045 moles of the acetic acid, and we will have some acetic acid left over after the reaction. So I'm actually going to use an ice table to describe this a little bit better, because I also want to show what's happening to the acetate ion at the same time. So when I take a look at this, I see that I have 0.0005 moles, this is moles, not molarity, of acetic acid, and 0.0045 moles of C2H3O2 negative. Now before I can turn this into an equilibrium problem, I have to change these moles into molarity. I had 45 milliliters being added to 50 milliliters, so that means I have a total of 95 milliliters. So I have to divide both these moles by 95 milliliters to get concentration. So now what I have is I have the concentration of the acid and the concentration of the conjugate base. I also, if I look back at my problem, have the Ka. So if I have Ka, the acid concentration, and the base concentration, that means I can use Henderson-Hasselbalch now. And I can start treating this like an equilibrium problem. So Henderson-Hasselbalch looks like this. Setup's going to look like this with our base on top, acid on bottom. And then pH is 5.70. Now, just like I told you last time, you could have also used an ice table, gone through and used an equilibrium expression and solved it that way, and that would be perfectly fine too. Either one of these are appropriate ways to solve this problem.